Behold a new dawn, not on Earth, but under the alien glow of an eternal orange sky. This is our audacious leap onto the rust-red sands of Mars. Witness the genesis of a new world, where impossible domes rise against towering, ancient mountains and humanity's tenacious spirit takes root. Here, within shimmering walls of glass and steel, life blossoms in verdant defiance. This is the epic saga of survival, the monumental struggle to carve out a pocket of Earth in the vast, silent cosmos. The Chinese greenhouse, the archetypal model for a humanity with a future. When we consider the future of humanity, be it in dizzying orbital habitats, on the dusty plains of Mars, or in the climate-ravaged regions of our own Earth, we are, at the core, thinking about one thing: resilience. The ability to create closed, self-sustaining systems that not only harbor life but allow it to thrive under the most extreme conditions. In this search for the perfect model of biospheric autonomy, it is worthwhile to look not only to the stars but also into the depths of our own agricultural history. There, in the seemingly simple architecture of the Chinese solar greenhouse, we find a genius and timeless archetype that more than ever must serve as the blueprint for the greenhouses of the future, because it is a masterpiece of passive efficiency. While modern high-tech greenhouses demand insatiable amounts of energy for heating, cooling, and lighting, the Chinese model understands the sun not only as a light source but as an architectural partner. Its south-facing, steeply inclined transparent surface, often double or even triple glazed, maximizes solar radiation in the winter months. The massive, insulated north wall of clay or concrete, however, acts as a gigantic thermal battery. It absorbs daytime heat and slowly releases it during the cold night. This simple dialectic of absorption and retention, of light trap and heat storage, creates an astonishingly stable microclimate with minimal external energy input. On Mars or the Moon, where every kilowatt-hour of energy is a precious commodity, this principle of passive climate control is not an option but a necessity for survival. Yet the true genius of this greenhouse lies in its multifunctional adaptability. It is not a rigid building but a living system. The massive back wall can serve as vertical growing space for climbing plants or often houses water tanks that further enhance the thermal mass effect. Simple, manually operated ventilation flaps on the front facade enable precise control of temperature and humidity. This low-tech robustness means low failure rates, easy maintenance, and independence from complex, vulnerable control systems. In an extraterrestrial colony, where spare parts are light years away, this mechanical simplicity and repairability are invaluable. The Chinese solar greenhouse teaches us a humble yet revolutionary lesson: the most advanced technology is not always the one with the most processors, but the one that operates in perfect harmony with the given physical and ecological principles. It is a system that prioritizes intelligence through design, not electronics. Chapter 1: ETFE Foil, the transparent skin. The outer shell of a passive greenhouse is more than just a cover. It is its first line of defense against the harsh external environment, and its primary tool for capturing and optimizing sunlight. In modern Chinese passive greenhouse design, the material of choice is often ETFE, ethylene tetrafluoroethylene, or PTFE, polytetrafluoroethylene, foil. These fluoropolymer films are lightweight, incredibly durable, and highly transparent, allowing the maximum amount of sunlight to penetrate the structure, while also maintaining excellent thermal insulation properties. ETFE and PTFE are both chemically inert, which makes them resistant to corrosion, UV radiation, and temperature extremes, qualities especially critical when managing extreme seasonal fluctuations. The foil is typically stretched over a metal or composite frame in a double or even triple layer, creating an air gap that functions as additional insulation. This layer of trapped air reduces heat loss dramatically, allowing the greenhouse to maintain a stable internal climate without the need for powered heating systems. The transparency of ETFE is another critical advantage. Unlike glass, which can block certain wavelengths of light, these films allow a broader spectrum of solar radiation to reach plants inside. This ensures optimal photosynthesis and accelerates plant growth. Furthermore, the foil can be coated with anti-reflective or hydrophobic layers, preventing dust accumulation and reducing maintenance needs. Installation is also highly practical. They can withstand extreme wind loads, hail, and even minor impacts without tearing, thanks to their elasticity. Over time, the material does not degrade significantly, meaning that maintenance cycles are long and predictable. In the context of a passive greenhouse, ETFE is not simply a covering, it is an active participant in the ecosystem. By capturing sunlight efficiently, reducing heat loss, and maintaining a protective barrier against external contaminants, the foil creates a microenvironment in which plants, microbes, and even small robotic systems can thrive. Its properties, combined with other structural and thermal components, make it a cornerstone of the greenhouse's sustainable operation. Chapter 2, Structural Frame, the Skeleton. The structural frame is the backbone of a Chinese passive greenhouse. It must support the weight of the outer foil, withstand environmental stresses, and integrate seamlessly with thermal systems, irrigation lines, and ventilation networks that in traditional designs. The frame is often made from steel or aluminum tubing, offering a combination of strength, flexibility, and corrosion resistance. Modern designs may also use composite materials that reduce weight while maintaining rigidity. The frame is engineered to form an optimized geometric shape, usually a cylindrical or semi-cylindrical tube, to maximize sunlight exposure and minimize wind resistance. The curvature allows snow or dust to slide off naturally, preventing buildup that could compromise structural integrity. Connection points are precision engineered to allow the ETFE/PTFE foil to be stretched tautly without sagging, ensuring even light diffusion and minimal thermal bridging. Beyond mechanical support, the frame integrates thermal mass elements. Heavy tanks or water-filled columns are anchored directly to the frame, ensuring stability and efficient heat exchange. The frame also serves as the conduit for water, electricity, and monitoring sensors, enabling automated systems to operate with minimal human intervention. Durability is paramount. Steel and aluminum frames are treated with coatings that prevent corrosion and UV damage. Joints are designed to handle expansion and contraction from temperature swings without warping. For regions prone to seismic activity, frames are anchored with flexible base plates to absorb shock, maintaining the integrity of the entire greenhouse. Finally, the frame must accommodate modularity. Modern passive greenhouses often use repeatable frame sections, allowing for scalable construction. This modular approach not only simplifies repairs but also facilitates future expansions or redesigns of internal components. The frame, while invisible to casual observers, is thus an essential player in maintaining the delicate balance of the greenhouse ecosystem. Chapter 3, Thermal Mass, the Heat Battery. In a Martian passive greenhouse, temperature regulation is less about active heating and more about intelligent storage and release of heat. This is where thermal mass comes into play. Unlike Earth, Mars has an extremely thin atmosphere and a wide range of temperature swings. Daytime can be relatively mild, but nights plunge into severe cold. The greenhouse's thermal mass is engineered to stabilize this environment, storing solar energy during the day and releasing it gradually at night. The system typically consists of large water tanks positioned along the back wall or sometimes within modular columns running through the greenhouse. Water is ideal because of its high specific heat capacity. It can absorb large amounts of heat without significant changes in temperature. During daylight hours, sunlight passing through the ETFE/PTFE film is absorbed by the tanks, which act as giant thermal batteries. The tanks may be coated or mirrored on the side facing the greenhouse interior to maximize heat reflection and retention while minimizing losses to the exterior. At night, when temperatures plummet, the stored heat radiates slowly back into the greenhouse, maintaining a survivable climate for plants, microbes, and human occupants. This passive system eliminates the need for electrical heating, reducing energy requirements and simplifying life support logistics. There are no moving parts, no pumps, and no reliance on power grids. The thermal mass operates purely according to the laws of physics. The design also anticipates potential emergencies. Water tanks are anchored securely to the structural frame, ensuring stability even during seismic activity or if the pressurized foil envelope is compromised. In modular greenhouses, tanks are positioned to allow easy maintenance or replacement without interrupting the entire system. Furthermore, temperature sensors are integrated to monitor heat distribution, allows the colony's automated systems to optimize environmental conditions efficiently. In essence, the thermal mass is not merely a passive component, it is the heart of the greenhouse's climate control. It converts sunlight into stored energy, smooths out temperature extremes, and ensures that life can continue unabated, even under the harshest Martian conditions. By marrying simplicity with efficiency, the thermal mass exemplifies the elegance of passive design, transforming physical principles into a vital lifeline. Chapter 4: Ventilation, the breath of the biotope. Effective ventilation is critical in a closed ecological life support system. On Mars, the thin atmosphere provides almost no buffer for gases, meaning oxygen, carbon dioxide, and humidity must be carefully regulated inside the greenhouse. Passive greenhouses rely on natural convection, but the Martian environment also necessitates auxiliary ducting, fans, and airflow channels integrated into the structural frame. Air circulation serves multiple purposes. It distributes heat evenly, prevents condensation on the ETFE/PTFE foil, ensures that carbon dioxide produced by humans is delivered to plants, and disperses oxygen from photosynthesis throughout the interior. Ventilation ducts are carefully routed along the internal frame, keeping the pressurized envelope undisturbed. Sensors continuously measure CO2, O2, and humidity levels, triggering microfans or adjustable vents as needed. The system is designed to maximize redundancy. Should one section fail, airflow is rerouted through alternate channels, preventing pockets of stagnant air. Filters are incorporated to remove dust and microbial contaminants, a precaution critical in a Martian environment where airborne particles can compromise plant health. The careful balance of ventilation ensures that plants grow efficiently, humans breathe safely, and the greenhouse maintains an equilibrium without overtaxing energy resources. Chapter 5: Algae Bioreactors, Oxygen and Radiation Shields. Algae bioreactors are multifunctional marvels in a Martian greenhouse. Positioned vertically along towers or walls, they generate oxygen through photosynthesis, provide nutrients for hydroponic systems, and serve as living radiation shields. Algae are highly efficient at converting light into energy, and their dense biomass absorbs harmful cosmic radiation, protecting both plants and humans. The bioreactors are integrated with lights, water, and sensors supported by the structural frame, allowing precise control over growth conditions. The system is self-reinforcing. Oxygen from algae sustains the colony, CO2 from humans feeds the algae, and harvested biomass cycles back into nutrient solutions. This closed-loop philosophy extends beyond life support into material production. The harvested algal biomass serves as a renewable feedstock for producing bioplastics essential to the Martian colony. Through on-site processing, such as extraction, fermentation, or thermochemical conversion, key components of the algae can be transformed, algal oils and lipids. These can be converted into bio-based polyesters like PHA, polyhydroxyalkanoates, or PLA, polylactic acid, suitable for 3D printing tools, spare parts, and rigid containers, proteins and polysaccharides, e.g., alginate. These can be processed into biodegradable films, binders, coatings, and flexible materials for packaging, medical supplies, and composite materials. Chapter 6: Reflective Shutters, Emergency Armor. reflective shutters are a critical component of the Martian passive greenhouse, designed to protect both the delicate ETFE film and the internal ecosystem during extreme environmental events. Under normal conditions, the shutters remain retracted, allowing unobstructed sunlight to reach the plants. When sensors detect sandstorms, high winds, or blocked sunlight, the shutters automatically deploy to shield the greenhouse. These shutters are multifunctional. In their primary mode, they roll down vertically over the sides of the ETFE envelope, acting like heavy-duty window shutters. However, in extreme situations, such as particularly violent storms, overflights of vehicles, or nearby landings where debris might be thrown, the shutters can also unroll horizontally over the dome, forming a protective insulating blanket across the entire greenhouse. This secondary mode shields the ETFE shell from abrasive dust and mechanical impacts, ensuring that even the most fragile parts of the structure remain intact. The system is designed in multiple layers, each serving a distinct purpose. The outer layer is robust and impact-resistant, absorbing collisions from small debris and providing mechanical protection. Beneath it lies an insulating layer, which minimizes heat loss during sudden drops in temperature, a frequent occurrence during Martian nights or prolonged storms. Finally, a highly reflective inner layer enhances internal light management. During periods when the greenhouse is fully enclosed, the reflective surface bounces artificial light from LED grow lamps back toward the plants, maintaining optimal photosynthesis levels even when sunlight is blocked. This ensures that both leafy greens and fruiting crops, such as tomatoes and peppers, continue to grow efficiently throughout extended periods of coverage. This combination of protection, insulation, and light management embodies the core philosophy of the Martian passive greenhouse. Every component serves multiple critical functions. The reflective shutters are not merely a defensive measure, they are an adaptive, multifunctional layer that transforms the greenhouse from a transparent, photon-collecting shell into a resilient, insulated, and efficiently illuminated life support system. In operation, the shutters integrate seamlessly with the structural frame and internal systems. They roll along precision tracks attached to the frame, ensuring smooth deployment without interfering with the pressurized ETFE envelope. When fully extended, the shutters complement the greenhouse's thermal mass tanks, trapping warmth and stabilizing internal temperatures. Ventilation systems continue to circulate air through filtered ducts, maintaining gas exchange for both plants and humans. LED lighting arrays within the greenhouse are automatically adjusted to maximize internal illumination, preventing photosynthetic deficiencies even during multi-day storms. In summary, the reflective shutters are an elegant fusion of protection, energy efficiency, and functional redundancy. They allow the greenhouse to withstand the most extreme Martian conditions while ensuring that internal life support systems, temperature regulation, air circulation, and photosynthetic lighting remain fully operational. In a landscape of rust-colored dust, high winds, and unrelenting solar radiation, these shutters transform the fragile greenhouse envelope into a robust, multifunctional survival skin, safeguarding both plants and humans alike.